understand. Why, if he's supposed to be like this super advanced robot, does he transform back into this piece of crap? Come here.
Oh, see, no, no, that doesn't work. See? Great, now, see? Fantastic. Now you pissed him off. That car is sensitive. I mean, $4,000 just drove off. What?
Alright, welcome to section 4.1. Today we're going to be talking about transformations, and not necessarily transformations in a cool Camaro type sense, but we're going to talk about graphical transformations as well as equation transformations. And in terms of math, transformations normally start off with what's called a parent function, and this is just the simplest form of a function or an equation. We went over about 12 or 14 of these in Unit 2, such as x squared. I think we talked about x cubed. We even did the square root of x, the absolute value of x, even that greatest integer function. Okay, so there were many more that we went over, but these 12 or 14 that we went over in Unit 2 are what are called parent functions. They are the simplest form. They really don't have any numbers or negatives in them. It's just a function in terms of an x. Now what we're going to do today is transform them in three specific ways, three specific fashions, I guess. And the first one that we're going to talk about is what's called a transformation by translation, meaning that we're going to move the function, we're going to translate the function either left or right, or up or down in terms of a graphical picture. But we also can transform the function as well. They're very related. So in terms of moving our function either up or down, that's what we would call a vertical shift. We're changing its vertical position either up or down. And in terms of our equation, this vertical shift kind of comes into play when either we're adding or subtracting on the outside of our function. Now when we go through this section, it's going to be kind of familiar for us because we've been doing these a lot this year actually, you just haven't realized it. So we're just going to kind of review what we've been doing in some of those lessons so far this year. So vertical shift is when we add or subtract on the outside of our function. Now a horizontal shift, that's meaning left or right. Again, we're going to be adding or subtracting, but this time that addition or subtraction is going to show up on the inside of our function, meaning inside parentheses or inside a square root, inside absolute value bars. These are going to be on the inside of our equation. And what's very special about this kind is that it kind of does the opposite of what you think. So it always moves opposite. So, for instance, if I were to add 7, maybe on the inside of this square root function here, it's actually going to move to the left 7. So even though I'm adding, we kind of have that intuitive sense that it would be moving to the right, it's actually going to move to the left. So this horizontal shift, you're going to see how we go through this lesson, the horizontal motions always move opposite of what you would think. So looking at an example down here, we have our basic parent function. Okay, we're starting with the quadratic, and we want to describe the translation. So what is this subtraction of 3 and subtraction of 5 actually doing to my graph? What is it doing to this parent function? Well, notice how we're subtracting 3 on the inside, so that would be some type of horizontal shift. And since it's a subtraction, it's going to do that opposite motion of what we would think. So intuitively, we would think it would move left, but it's actually moving to the right 3. Maybe we'll say 3 units. Now the minus 5, notice how that's on the outside of our function. It's no longer inside those parentheses, it's kind of tacked on the end. This would be describing a vertical shift, and since it's subtracting, this one does kind of what you would think it would do. It would move down 5 units. Okay, because we have that vertical shift, it's going to either move up or down. Since it's negative or subtracting, we're moving down. So graphically speaking, what's going on here is that we have this parent function starting at the origin, this parabola here, and what we're doing is we're shifting or translating this graph right 3 and down 5. So we're simply just moving that vertex point. We're not really changing the wideness or anything of this U, we're just changing the position on the graph. So the new vertex, if I moved it right 3, it would be positive, and if I moved it down 5, we would have a negative 5. So notice how the vertex in this parabola is very related to the translation in the actual equation of this new graph. Now over here we're going to do something a little bit different. Instead of describing the transformations or the translations, we're actually going to write them in our parent function. So dealing with the square root, we want to write the function with a vertical shift up 5. So vertical shift is going to be on the outside of our function, and since it's going up, we need a plus 5. But we also need a horizontal shift, so that would be on the inside of our square root. But since it's going left 17, I need the opposite of what I would think. Since it's going left, that means I actually need an addition in my equation. So if we look at our function, we have a square root of x. I need an addition of 17 on the inside. So let's make sure it's underneath our square root bar. But I also need an addition of 5 on the outside for that vertical shift. So that's just going to be tacked on the end. So there's our function with these specific translations. What I want to do is show you this little visual down here, and in order to see it, I'm going to have to erase what I have here. So just pause the video and take a second to make sure you have everything you want down in your notes. Alright, so let's take a look at this little animation thing right here. Alright, so we're specifically dealing with a parabola, this U shape, and we've seen these A's, H's, and K's so far in some of the other lessons where we've been writing the equations of these translated graphs very similarly to what we just did. But notice how in this H instance, if I make my H a positive number, okay, for instance 3.1, notice how it moves it to the right, but in the equation, it's actually a subtraction. That's why we have this opposite of what we think, because the normal general equation up here is that we subtract this h value. We're subtracting this change in x. So even though it's positive, we're moving it to the right. In the equation, it's actually negative. Now, if we go the other direction, if I move it left to 4.1, if you subtract a negative, that's changing your equation to a plus. So again, we have that opposite of what we would think. Even though we're moving it to the left in our equation, it's actually showing that plus. Now the k value on the other hand, that value that's on the end is our vertical motion. So if we were to just add on 2.8, notice how it just moves up. But if we were to subtract 3.5, notice how it moves down. So the outside does what you think, but the inside is always that opposite motion. I hope that helps us out a little bit. Alright, so now that we can move our graphs and equations left, right, and up and down, let's talk about how we can transform their scale, meaning making everything bigger or smaller. We're either going to make them really large or really thin. We're going to talk about moving or transforming this scale. So in terms of a vertical stretch or shrink, almost like an accordion is what I think about in this case, and as well as the horizontal. A vertical stretch is going to happen when we have a value bigger than 1. Okay, we're going to call this value A in a little bit. But in terms of a shrink, our A value is less than 1. And again, this makes sense. Remember, the vertical changes are always going to make sense. Just like if we moved up or down, it was plus or minus, that makes sense. If we're going to stretch it, we're going to need a value bigger than 1. That makes sense. If we're going to shrink it, we're going to need a small value, smaller than 1. That makes sense as well. And just like in the other instance, when we added or subtracted on the outside, this time when we're talking about changing the scale, we're going to be multiplying on the outside. So addition and subtraction translate our graph up or down, but when we multiply on the outside, we're going to be stretching or shrinking it in some way. Now, in a horizontal sense, remember, it's the opposite of what we would think. So our A value for a stretch is actually smaller than 1, and our A value for a shrink is going to be bigger than 1. Again, opposite of what you think. And just like in the translation, if we're moving something horizontally, it's on the inside of our function. So this time we would be multiplying on the inside of our function. Alright, so let's just take a look at some examples here. We're going to start with our basic quadratic function, and we have these translations or transformations. Notice how this would actually move it right 3 and down 5, just like we had before. But this time we have this multiplication out front, and notice how it's on the outside. It's no longer inside those parentheses like this minus 3 was. So maybe I'll get rid of these for now. So in this case, we're specifically multiplying by something on the outside of our function. So that means it's going to be some type of vertical stretch or shrink. So we got to take a look at our value. Okay, this is considered our A value. This was our H. This was our K. The number out front is considered our A value. So notice how the A is bigger than 1, so we're specifically vertically stretching our graph, what we would say by a factor of 4. Okay, factor meaning multiply. So we could say vertical stretch, if I can spell, by factor of 4. Now it's just asking us to describe the scale. If it said to describe all the transformations, you'd also have to throw in the right 3 and down 5 motion, but it's just asking for the scale, so that's all we're focusing on in here. Now this one down here gets a little tricky. Okay, notice how we are multiplying by 2 in terms of our x value. We're multiplying by 2 on the inside of our function. So this is going to be some type of horizontal stretch or shrink. But what we got to do is kind of separate this because this 2 is also affecting this 8. Notice how if I were to factor out a 2, okay, from both the 2x and the 8, I would be left with an x minus 4 squared. And I have the minus 5. So this is where we got to be careful because the 2 is still on the inside of these parentheses. So I got to make sure that the 2 is still on the inside of these parentheses. Now I got to throw in this extra pair to kind of denote that the 2 is still on this inside. So what we got to do here is notice how this 2, since it's on the inside of the parentheses, would be some type of horizontal stretch and shrink. But now that we factored it out, notice how it is no longer a right motion of 8, it's actually a right motion of 4. So we got to be careful with this because we need to factor out this inner factor of 2 in order to find this correct horizontal motion. So we got to factor out that 2. Now since it's on the inside, that means we're going to have some type of horizontal stretch or shrink. Notice how the A value is bigger than 1, so it's actually going to shrink our graph. Okay, kind of hard for us to figure out because a big number kind of means that it would stretch it, but remember the horizontals always do the opposite of what we would think. So this is actually going to be a horizontal shrink. And this time we would say by a factor, and this is what gets crazy, by a factor of 1/2. Okay, again, opposite of what we think. Since our A value is bigger than 1, that's why we're calling in the shrink. But in terms of a graphical relationship, it's shrinking it by a half. We got to find the reciprocal. If I can spell that right, reciprocal of this horizontal motion here. And again, we're going to have a little diagram down here to help us out, but for now, this is the relationship between a horizontal shrink. Even with a stretch, we would find that reciprocal in this motion. So this one can be very tricky for us because it's that horizontal stretch or shrink. It does the opposite of what you'd think, and you got to find that reciprocal. So let's just take a look at an example here. We have the given parent function and we want to fill in a vertical shift of down 5 and a horizontal shrink by a factor of 1/3. Okay, now notice how that is very similar to what we did over here. We said a horizontal shrink by a factor of 1/2, but the actual number that showed up in our equation was a whole number of 2. So if this is the description, a horizontal shrink by a factor of 1/3, that means I need to find the reciprocal to make sure I put in the correct number in my equation. So we got to find the reciprocal here, which would just be the number 3. So if we take a look at this, if it's a horizontal shrink, that means it needs to be a multiplication on the inside of our function. So if we're looking at this x to the third, I need to multiply my x value by 3, and I need to make sure it's on the inside of these parentheses. So I can close off with that cube on the outside. But I also have a vertical shift of down 5. So on the outside of my equation, I need that subtraction of 5. Remember, shifts go up or down, left or right, but stretches and shrinks are those scale factors either on the inside or outside of our equation. Now down here, we're going to write another function with a horizontal shift, right 2. So that means I need to be subtracting on the inside. A vertical shift up 3, so I got to be adding on the outside, and a vertical stretch, so that means multiplication by a factor of 4. Now since it's a vertical, I don't need to worry about this reciprocal nonsense like we did down here in the horizontal. The verticals do exactly what we would think. So if we were to write our function for our cubic, we need a multiply by 4 on the outside, so let's just put that first. Then on the inside, I need this subtraction of 2. We still need that cube. But on the outside, I need the shift up 3. So let's add a 3 on the end. Okay, so here's our right 2 motion, our up 3 motion, and our vertical stretch by a factor of 4. Now again, I need to erase some of this so I can show you a visual here, so make sure you get down what you want to get down. And it would help if my eraser was bigger. There we go. Alright, so let's try to make sense of this stretching business here. Maybe I'll need to erase some of this too. Okay, so instead of the parabola, we're actually going to take a look at a sine graph. Those were one of our parent functions from before. And we already dealt with the h's and k's, but this time we're dealing with these a's and b values. Now, since the a is on the outside, this is considered our vertical stretch or shrink. And in this case, the b value is on the inside of our parentheses, so this is our horizontal stretch or shrink. So notice how my a value right now is 1. If I multiply by a bigger number, maybe 2.2 or 3.5. Okay, so there's my 3.5 being multiplied right out front. Notice how it's vertically stretching our graph. Okay, we no longer have an absolute max right here at a value of 1. It's being stretched up to a 3.5. Same thing down here, an absolute min at -1 is being stretched down to a negative 3.5, it looks like. So we're only changing the vertical motion of our graph. Notice how the x-intercepts stayed the same. Okay, those technically do not have a height. Their height is a y value of 0. So I can't change or multiply by 3.5 times 0, would just leave that point where it is. But if I take this height of 1 times 3.5, that's going to give me a new height of 3.5. So we're just changing the vertical motion of our graph. We're not changing it in terms of these x-intercepts either left or right. So maybe we'll go back to 1. Try to get it as close as I can. Alright, now let's change the horizontal. Okay, so notice how when my b value gets bigger, my graph is actually shrinking. Okay, it's actually coming in towards each other. So again, now in this case, our height is not changing because we're not stretching it vertically. We're actually stretching it horizontally. So in this case, we had a normal factor or a normal value of it looks like 3 right there, but we're shrinking it all the way down to this factor almost by 1. Okay, it's almost like we're taking 3 and dividing it by this value or b value of close to 3 to give us a new value of 1. Okay, that's the reciprocal motion. So instead of multiplying by what we would say 1 over 3 in this case, because that would be the reciprocal, we're essentially dividing by 3. It's going from a 3 all the way down to a 1. 3 divided by 3 is 1. But notice how, again, if my b value is smaller than 1, maybe 0.6, our graph is extremely stretched out. So again, we're starting at 1. We're starting here at 3, and this is about 0.5, which means that the reciprocal would be 2. So notice how if I kind of start at 3 and multiply it by 2, it's being stretched out almost very closely to a value of 6 out here. So the reciprocal only comes into play when we're talking about this horizontal stretch or shrink motion. So a small value actually makes it wider, whereas a big value actually makes it smaller, almost like an accordion. It's really shrunk tight together. So again, hopefully that visual really helps us out. Alright, so our third and final transformation that we're going to go over today is what is called a reflection. So we've done the translations either up, right, left, or down. We talked about the scales, maybe stretching it or shrinking it, either vertically or horizontally. But now we can make some reflections, meaning we're going to flip it across some of these axes. So we're going to flip it across the x-axis when we have a negative, maybe you actually write out negative so that doesn't mean subtraction, a negative on the outside. And about the y-axis, again, this would be a negative, but instead of on the outside of our function, it's going to be on the inside. So what do I mean by that? This is a square root graph. It's been translated. It looks like 3 to the right and up 2. So if we were to write that square root, 3 to the right would be a positive 3. And then up 2 would be a plus 2. Now if I wanted to flip it across the x-axis, I would need a minus on the outside. And what that's going to do is flip all of these points down here. So notice how this point is 2 units above the x-axis. That means if I flip it, it's now going to be 2 units below it. And it looks like this one over here is 4 units above the x-axis, which means if I flip it over, it should be 4 units below it. 1, 2, 3, maybe somewhere right there. There we go. So this would be our translation here, and then we would have this negative on the outside. So then over here we have about the y-axis. So this would mean a negative on the inside of our function. And just like before, we want to make sure that it's factored out. We have a negative on the inside of our function. So these points, instead of flipping them across the x-axis, we're going to have them reflected across the y-axis. So if this one is 3 units to the right of this y-axis, if I flip it over, it needs to be 3 units to the left. Somewhere right there. And then if this one, it looks like is 1, 2, 3, 4, 5, 6, 7 units to the right, it would have to be 7 units to the left. So we can get that motion. So depending on where your negative is, you're either flipping it over the x-axis or over the y-axis. And what's important about these reflections, okay, maybe star note here, is that these are always done first. So when we get to an example at the end to try to do on our own or maybe together, we always do reflections first. Okay, big star idea. Alright, so down here let's describe the reflection. We could easily say this goes right 3, down 5, and it has a vertical stretch by a factor of 4 based on what we've been doing so far. But the reflection is just that negative, how is it flipping? So since this negative is on the outside, we would say it would be a reflection across the x-axis. Now this one, on the other hand, notice how our x is negative on the inside. So if we were to try to factor this to actually show it, we would have a negative. If I factored out an x or a negative out of everything, the negative x would become a positive, and the 4 would become a negative. So we would have that whole thing squared. Okay, just like how we had to factor out that scale, we might have to factor out this negative to help us out. And notice how, again, since it was originally on the inside, we still have those parentheses showing how it's on the inside. So in terms of this new graph, just rearranging a negative, factoring it out, this graph would go right 4, down 5, vertical stretch by a factor of 2, but since the negative is on the inside, it's actually being reflected across the y-axis. Alright, so let's try writing some equations here. We are taking a look at an absolute value. We want a vertical shift of up 1, so we got to add that on the outside. And we want to reflect it across the x-axis. Okay, so that means a negative, and if it's across the x-axis, it has to be on the outside. So let's put our negative on the outside. We have our absolute value of x. but a shift of up 1, we need to add 1 on the outside. There we go. Now let's try this one. We have a vertical or horizontal shift left 2, so that means we got to add. Okay, horizontals always do the opposite of what you would think. We got to add that on the inside. Vertical stretch by a factor of 5 means multiply on the outside. And a reflection across the y-axis, so that is a negative on the inside of our function. So if we were to put all of that together, let's see, we have a vertical stretch by a factor of 5. So multiplication of 5 on the outside, normally out front, that's where it goes. Then we have our absolute value sign and our variable. We need to add 2 on the inside. So let's add 2. There we go. And, oh, I forgot to put in the minus on the inside as well. So this would actually be, maybe, let me rewrite this for a second. We need the minus of an x and this plus 2. Very similar to how we did over here. The negative's on the inside, but what else is on the inside should be showing the correct transformation. So here's what you could actually write. But what else? You could actually, maybe if you wanted to distribute in the negative, you don't have to do that if you want to, or if you don't want to. If you did do that, if we distributed in the negative, it would be a negative x and a minus 2. But again, in order to see the correct transformations, you'd eventually have to factor it out anyway and get back here. So if you wanted to distribute it in, you could. It would look something like this. But leaving it outside, I think, really helps us visualize or see that reflection across that x-axis or across the y-axis. But it also really helps us to see this horizontal shift of a left 2. Because if you were not to factor out that negative, you might think that it would be going right 2, but it is in fact going left 2 because you need to factor that out. Alright, so let's get in a general sense here and just take a look at these different parent functions that we talked about from Unit 2. Just to kind of review, the a value we said was that vertical stretch or shrink where we're either multiplying on the outside by something. The b value is this horizontal stretch or shrink when we're multiplying on the inside. Our h is our translation either left or right, or the k value is that translation up or down. So in terms of a quadratic function, we have our parent shape or our parent graph starting at the origin, and then the vertex is actually where this h and k are used. So when you start to translate either up or down or left or right, this is the particular point that you want to try to start with, because if you move this one first, it's going to make all the other ones really easy to place or move as well. So we have our general form for our transformations for a quadratic function, but remember you might have to factor out a number, this b value, if there is a horizontal stretch or shrink. So I wanted to write both of these down. I kind of ran out of room on your note guide to do that, but I think I left you enough room to write these underneath the ones that are on your note guide. So this is the general form, but you may have that horizontal stretch or shrink. In that case, it would look like this. Now for a cubic, we would consider, it doesn't really have a vertex like the quadratic one does, but we would use the origin point as our starting h and k value and then move the other points. It will have this general form based on the transformations, but again you might have to factor out that b value if you have that horizontal stretch or shrink. Absolute value functions have a vertex. They have this h and k value. Again, this is where you're going to start, but if you do have that b value, you got to factor it out as well. And for square roots, our starting value is going to be right at the origin, that starting point. You have your basic function here, but again, you might have to pull out or factor out that b value in case you have that horizontal stretch or shrink. So I guess the gist of this is to always start with this h or k point. Either it's normally right at the origin. Notice how this one's at the origin, this one is, and that one is actually. They're all at the origin. So start with that beginning point on your parent function and move it. And then try to move the other ones as well. If we take a look at some other ones, we talked about the exponential function, logarithmic, greatest integer, and rational as well. These ones are tricky because they don't always start at the origin. In this case, the exponential function starts at this first point at 0, 1. So that would be our starting point. Again, you might have to factor out a b value for that horizontal stretch or shrink. The logarithmic function starts at 1, 0, that h and k. Again, you might have to factor out a b value, so if you do, this is what your equation would look like. The greatest integer actually starts at the origin, so that's nice to know. And what's going on with the rational is that we specifically focus on the asymptotes in this graph, and notice how the asymptotes actually intersect at this origin. So where they intersect is our h and k value. So we're actually moving the asymptotes in this particular instance. We're not really moving the graph itself. The graph moves along with the asymptotes. So if we move the asymptotes, we're essentially moving the graph as well. And again, if you factor out that b value from what's considered the inside of your fraction here, or that denominator, you would get this particular function. So just some things to know. I think that these are really going to help us out when we go through the practice problems, trying to make sure that our equation actually matches the graph that we have. Alright, so we're going to put everything together in order to help us graph the following square root function based on its transformations. And if we need to, we can use a table of values to kind of help us out. So our rules for graphing, I said that we always start with the reflection, so we want to do that first. And then we're just going to go through the stretching motion and then the translate. So if you kind of want to look at this and think about RST to help you out, might be a good way to remember that. And whenever I hear RST, I always think about Pat Sajak from The Wheel of Fortune.
Phrase is the category tonight, R-S-T-L-N-E. Well, we start with the phrase.
Alright, so RSTLNE, we're using those RSTs to help us with these graphical transformations. So let's just go through and kind of label these different transformations to help us out. We have a negative on the outside of our graph, so this is the reflection that we want to start with, and that specifically, since on the outside is going over our x-axis. We are also multiplying by 2 on the outside, so that would be our vertical stretch in this case, by a factor of 2. Since we are adding 1 on the inside, remember it does the opposite of what we think, it's actually going to the left 1. Left 1, there we go. And minus 3 on the outside, this is going down 3. So there's our different transformations. We want to apply those to our parent function, and if we look at our equation, our parent function would be this square root value. So what I'm going to do is just plot the parent function first. Okay, the square root of x starts at the origin. If I were to put in 1, okay, the square root of 1 is 1, so I can plot that point. I also want to be strategic because I know the square root of 2 and the square root of 3 aren't really good numbers to plot on here. So we can put in the square root of 4, which would actually give us 2. So here is our parent function. We are going to transform it based on these transformations. Okay, so I made my dots really big because these are the points that we are going to be moving. So our first type of our transformation here is the reflection across the x-axis. So I'm going to use a different color just to show this transformation. We're going to move all of these points across this x-axis. Well, our first point is already on the x-axis, so it's not going to go anywhere. But since this point is 1 above the x-axis, when I reflect it, it's now going to be 1 below. And if this one is 2 above, when I reflect it, that means it's going to be 2 below. So let's do that. So here's that transformation based on that reflection. Alright, so now that we already did the reflection, maybe we'll cross that off our list, now it's time to do some stretching. Okay, so we have a vertical stretch by a factor of 2. So we're going to focus on the vertical heights of these points and multiply them by 2. So if we're taking a look at the vertical heights, that means we want to focus on this y-axis, or these y values of these points. This first point is at the origin, meaning the y value is 0. So if I were to take 0 times 2, it's still 0, so this point is not going to move. So maybe in blue, we'll keep that point right there. But notice how this point has a y value of -2, or -1 rather. If I multiply it by the factor of 2, -1 times 2 is -2. So this point's going to move down to that -2 position, somewhere right there. And this point has a height, we would say, of -2. So -2 times 2 would give me a -4. This point needs to move down to that -4 height, somewhere right there. So we'll connect those dots And there's our graph. So notice how we're vertically stretching it. It's like we're pulling all of the points down by a certain factor. Okay, we're stretching it in this case downwards, which is a vertical motion. So let's cross off our stretch. Now comes the translating. Okay, so we want to translate, we want to move all of these points left 1, but also down 3. So this was our H and K. Let's start with this point first, right at the origin, or that original one from the parent graph. We're going to move left 1 and down 3. So there's that new point. Now we want to move this one as well, left 1, down 3. And then this one, left 1, down 3. A little bit off our graph, but we can still take a guess about where it would be. So there is our transformed graph. We went through the reflection, the stretch, and the final translation. So this would be the actual picture, the actual graph we want. We could essentially erase all the other ones. I mean, they helped us get here, but this is the graph that we're specifically looking for. So, I mean, you could always test it in your calculator to see if you're right. Okay, hopefully you should be. Your graph should look something like this. Now, if we wanted to check it algebraically, we could use a table to help us out. And we want to plot points around this HK value. So that's kind of around this value of -1 right here. So if we were to make a table, our x value is -1. And if we just plot points around this -1, maybe we'll put in 0 and 3 as well. Just picking some points. Because notice how I want to check to see when this x is 0 that I get this value of -5, and when x is 3 I better make sure I get this y value I think is -7. So let's check to see if these points that we found based on the transformations are actually correct. So if we put in -1 into our x value here, -1 plus 1 is 0, the square root of 0 is 0, times -2 is 0, and minus 3 gives us a -3. And if we check out this ordered pair on our graph, notice how that's exactly where this first point is. So far, our graph is checking out. Now let's put in 0. 0 plus 1 is 1. The square root of 1 is 1. 1 times -2 is -2. And if I subtract 3, I get a -5. If I were to check this point to see if it's actually on my graph, 0, -5 is right there. So far so good. Again, our graph is checking out. If we check 3, 3 plus 1 is 4, the square root of 4 is 2, times -2 is -4, and if we subtract 3, we get -7. If we check it on our transformed graph, that's somewhere right there. So since all of our points are checking out, okay, we're checking to make sure that they actually work in our equation, then we can assume that this transformed graph is correct. Okay, so RST, very big idea. And also remember, everything inside those grouping symbols is a horizontal motion and always the opposite of what you think. Okay, the inside stuff, always opposite of what you think. But the outside, very easy to remember, it's always vertical and it always does what you think. I know it can kind of be tricky, but I guarantee you the more we do of these, the better it's going to be and the more it's actually going to make sense. So it might be a little confusing now, but believe me, we're going to get really good at these, alright? So enjoy these transformations, maybe go home and watch Transformers. Great movie, great series. So I'll see you guys next class.